Hello friends, welcome to the week 7 class, the recorded class for this week. So this week, after studying the types of elements and the types of materials and the meshing techniques, we come to the one of the most important topics in crashworthiness analysis, that is interface and contact modeling. So interfaces are defined so that the the parts would know how to interact with each other. So typically, in imagine in a crash analysis case that when you have a barrier on one side and you have a car impacting into the barrier, and only the frontal portion of the car is coming into contact with the barrier. What about the rest of the parts in the car? They are stacking up against the frontal parts so that the intrusion is felt inside. This is how it typically happens in the physical world as well. But what if there was no interaction between these all of these? Then in that case, what would happen is these red compounds would simply impact into the barrier. That is not really physical. So to represent this in FEA world, the interface are modeled or contacts are modeled. Now, when we are studying interface modeling in Radioss, the four most important things we'll look at is first of all the interface penalty method and the major three types of contacts, that is type 7, type 11 and type 24. Now type 7 contact is mainly known for having the variable stiffness and being a node to surface contact, whereas type 11 again is known for variable stiffness and it is edge to edge contact. Now we'll see what those things mean. And type 24 is linear stiffness against the variable stiffness of previous two, and it is a combination of node to surface and surface to surface contact. So we'll first of all go with the penalty method used in the interfaces. So if if we have a if we have a surface, and whenever there is another part trying to contact or trying in contact with this red part, what happens is first of all we have a segment, and there is a gap defined around that segment. Now this gap could be the thickness of the part. So imagine you have a mid shell surface or mid surface shell, and it has some thickness applied to it, and that thickness could be on the other side as well. So once some node of other part component comes into this range of the thickness, what would happen is that ideally this node should be pushed out of these thickness boundaries, so that still remains physical. Now in this picture, what we'll call this green node as a non-penetrated node, whereas the node which comes into the thickness zone or the gap zone, we'll call that a penetrated slave node. So when this node comes into the zone, there is a spring element that is forming between this particular surface and the node, and the spring element, as it gets compressed, as the penetration increases, the spring element is going to expand and it will push out that node out of this gap zone. Now if you remember how the springs work just from our last session of on 1D elements, as the spring goes on compressing, it is going to uh, increase the stresses or the opposing forces, and those forces will be responsible for taking the node out. Now obviously while doing this operation there will be some energies involved, and now that could hint to one of the energy errors that we look at in the out files. Now imagine that in this case there was only one node coming into contact with this particular surface segment. Now if there are multiple nodes coming into contact with this particular surface or a even bigger surface, imagine the kind of interaction happening at one moment. So what should happen ideally is that the algorithm in the solver should continuously look for all the nodes that are coming inside this zone. Then it should form these spring elements, and then it should instantaneously calculate whatever is the length of the current spring element is, and it should decide how much push force or push out force should be applied on that particular slave node. Now in this case, segment is being the master and the node which is coming into contact is being the slave, and the slave will follow whatever the master says. Slave will follow whatever uh, opposing force is applied by the master surface, and that is why the term comes as slave and the master. Now, if we have understood this, let's look at the three main scenarios of a contact. First of all, node to surface, the one which we just saw, that there is some surface and the nodes. So there is another component, but only the nodes are considered on that surface coming into contact with the main or master surface. Now, in this case, though the nodes coming into contact with the master are lying on that particular surface, the mesh lines may be neglected. Now that could be one of the limitation, but we'll see how that works out when we study some of the contact types. Then there is surface to surface, where surfaces as well as whatever so nodes as well as whatever lies in between the nodes, such as surfaces or the lines, even those are considered to be coming into contact with each other, and that way it becomes little more physical, little more sensible to understand. Then there is self contact, or another type of node to surface, where a part is deforming so much that its own nodes are coming into contact with its rest of the component. So typically buckling failure, the failure which we saw in our very first assignment, where the link was deforming so much and we were studying the hourglass on that. So that is one typical example of self contact, where the nodes of a part itself were coming in contact with the rest of the nodes. Now that case might be called as node to surface or surface to surface as well. So that becomes another variation. Now we'll take on the first variation, in this case, the node to surface contact. But before that, just to summarize what all things we are going to look at in this particular interface chapter, for cross structure applications, the main types of contacts which we usually study are type 7, type 11, and type 24, which we are going to study anyway. And then there is another type 2 contact, tied node to surface. Now that is little related to what we studied in the last session, the 1D elements, and it is also little more related to spot welds as well, which we'll be studying in the very next session on kinematic conditions. So first of all, we'll focus on type 7 contact. We'll study type 7 contact in much more details, and then jumping to type 11 and type 24 will become very easy, because once you understand how type 7 works, type 11 and type 24 are pretty easy to pick up. And then apart from that, there are other applications inside Radioss, and rest of the contact types go on to that. All right, so we just saw how type 7, type 11, and type 24 are going to differ from each other. Now this particular table over here, it mentions about slave and master and gap and stiffness and where it is used. We'll be looking at these in a short while. First of all, we have already understood what slave would mean and what master would mean. Slave is someone which follows the order of a master. So slave comes into contact with the master. Master creates that spring element which will push out the slave node out of the master surface vicinity, and that creates the opposing force on the slave part, and that is how the contact is going to work. So that is why the gap zone is defined all the time for this particular surface. The stiffness, again non-linear, because it is a spring element, and as we studied in the 1D element, an ideal spring, its stiffness should ideally increase as it goes on compressing. So non-linear stiffness. Again, with line to line contact, very similar things. So once we study type 7 in detail, type 11 will be very easier to pick up, and type 24, again, it is much more like combination of these two. If you have a solid element, obviously there will not be any gap as such, because solid element surface itself represent its boundaries against shell surfaces, where shell is actually having a thickness around it, and that is why this gap should be defined around it. so that non-physical relation doesn't happen. All right, and then stiffness in this case stays linear, unlike these two. Okay, so focusing on type 7, as I mentioned earlier, it is a node to surface contact, a general purpose interface, and it can simulate almost all types of contacts inside a structural crashworthiness analysis. So whether you have different parts meeting in different directions or different orientations, type 7 happens to be the most common solution. And that is mainly because it is non-oriented, and slave nodes can belong to any of the master surface or the slave surface. So that gives us the freedom that even the auto impact, or let's say the self impact, is also possible in this case. So the case which we saw for the hourglass issue, the one where the link was bending or deforming so much under buckling failure that it was stacking up against itself, and that is a typical case of how type 7 contact can be used. Now, we already saw how the interface would work in an ideal manner when the nodes, slave nodes, are coming into contact with master surface, and then slave nodes will be pushed out. It works on the exact same principle. That is why a gap is defined around the master. As long as it is a shell, it always needs a gap. Now that gap, well, that is a part of this card. Whether we can decide whether that gap can be constant or it can be variable depending on how the situation is. And then the resistive forces can either keep the nodes at the certain location, or they can keep the nodes always out of the vicinity. Now that also can be decided using the contact card, and that will be something really interesting to look at whenever we are looking at a variety of contact scenarios. And then because there are 1D elements forming, or the spring elements forming, while creating the penalty for the stiffness method, this interface has its own time step. So that is why I was trying to point out in the last session that you should understand how the 1D element are calculating the time step or contributing to the time step. So this interface has its own time step, and that is all because of that spring element that is forming while creating this contact or creating this push force. So this spring element time step would all depend on its length and the stiffness and density. Now the stiffness and density is actually considered from the two meeting components, and a minimum of those two is taken into consider for time step consideration. So if using the property of let's say master surface, if the time step is lower as compared to the slave surface, then it will also always consider the time step from the master surface. So it always goes for the worst case somehow, and that is the way it goes, because it wants to stay with at most accuracy, and lower the time step, it can reach for more accuracy. So that is the main reason why the interface time step can be very small at times, and that is because usually the thicknesses of the components are 2 mm or 3 mm. That means that the spring element could also be around 2 or 3 mm, or at the most 4 mm. Now we have already studied that if we have a steel components meeting on the both sides, then the minimum length of the element to meet our 5.5 microsecond time step could have been 5 or 6 mm. Now if that spring element length is even less than that, then obviously the time step is going to be lower in for that particular contact, and that is the whole and sole reason why the time step would drop down at the contact surfaces. And that is exactly what it is trying to explain on this slide. So this energy jump, whenever the slave node is approaching a master surface, uh, once it once it enters the vicinity, or that gap zone, there is a push force or a resistive force that is acting on that slave node. Now, to create this push force, there is an energy used from the system, and that can in fact tell you why there is a energy deficiency in the system. Because if you see that the energy error is negative, that could mean that some of the energy is being used for the contact, so that the slave nodes could be kept out of the vicinity. So this is how you know where the energy might be going out, and this is how you know that how to rectify some of the energy errors. Now, obviously, there are parts which are going to come into contact, and now to mitigate that, it is always not always affordable to lose out on energy or lose out on energy error. So this energy jump would obviously happen only in the beginning stage, where if you have while loading in the first time itself, if the node is in the vicinity of the master gap, then at the initial stage itself, the solver will try to push out. Now that is exactly when the energy jump would happen. If in the later stages, when the slave surface is approaching the master surface, because of the contact algorithm, when it is trying to locate all the nodes which are reaching towards the master, and it is trying to understand if any node is coming into contact with this, in that case the energy jump is so low, or it is so less or so negligible, that all the nodes are stopped right here and there, right here at the border, and that is why there is no further energy that needs to be spent in pushing out those nodes. And that is why once you have all the penetrations, or all the nodes out of this zone, the energy will be the energy error after that will be very less. Now, obviously, as I mentioned before, just like an ideal spring element, the type 7 interface, the resistive force has a characteristics that it increases with the penetration. Now, now how that penetration works, we'll see in the next slides very shortly. And then one another highlight from this is that the gap is used on both sides. So there are few contact definitions which we are not even studying right now, but there are few contact definitions where if there is the master if there is master surface as the mid surface shell, then the for the contact purpose, it creates this master gap only on one side of the surface and not on the other side. And that is not really physical again, because if you have this as a master and this as a slave, it is not always obvious that slave would reach only from this side. It could reach from the sides, or it could reach from the other side as well, depending on how the slave surface is oriented. Now in those cases, it is ideal to have master gap on both sides. But in general sense, it is a very good idea to have the master gap on both sides, and that is one advantage what type 7 contact is providing us. Now, whenever we are trying to define a type 7 interface card inside Radioss, in HyperCrash or even in HyperMesh, you see a bunch of parameters which it is trying to ask us. Now, many of them are not always required, so we'll study only those which are very important to define any contact. And then there are other elements or other entities which can be defined later on if need be. So once you study these, the list which I have mentioned here, you will exactly understand why rest of them are not really useful. Now, such as now iBag here won't be mentioned in the important features, because iBag is actually more relevant to airbag definitions. Now, airbag is something that is not really part of crash structure, but it is more a part of occupant safety, which is again a crash safety application, but it is a different scenario altogether. So that is where it is more useful. Here, we don't have to really worry about those, so we can keep those 0 or default whatever it asks for, just to neglect its effect. So, first of all, iGap. which determines how the size of the gap is going to be calculated. So just as what we saw, there is a gap portion or the vicinity around the master surface, which is going to be defined to decide whether the slave node is has approached on the border or whether it is inside the vicinity already or not. So there are different methods of calculating how the gap should be defined, and we can have a control on that as well. Then there is a minimum gap for activation of interface. So that means that we can simply tell the solver that if the slave node reaches within zero point 0.5 mm of my master surface, which is mid surface of the master, if it reaches within that distance, just activate the contact and just push out that node. Now that is also another idea of defining this, that really solves the rest of the calculations. The solver doesn't have to calculate what the I gap is or what the initial gap is. It just has to worry about that minimum gap. As long as the slave nodes are out of that minimum gap, we should be good to go. It doesn't matter what the thickness is. That may not be physical or real or practical all the time, but it has some application. Now then there is inacti, uh, that tells us about what action should be taken if the initial penetrations exist. Now, as I have mentioned earlier, that there could be energy jump in the initial stages if the slave nodes are within the vicinity already. Now this inacti is going to help us with that. iStiff, it tells us or it helps us decide how the stiffness of the interface is going to be calculated. As I mentioned earlier, in a general purpose or general sense, the stiffness of the contact would all depend on the stiffness of the spring. And now typically for type 7 contact, stiffness of the spring would depend on how much penetration is happening. So more the penetration, higher the stiffness, and that exactly runs how the iStiff is going to behave. Now there are different options inside that. You can have viscous factors involved as well. Not really needed in the crash applications, but it is available as an option for some other applications inside Radioss. Then there is I-form, friction formulation. So obviously when two parts are coming into contact, there is obvious friction between them. The contact may not always be normal, but if there is any sliding action between them, the friction will be another significant parameter to look at. Then there is minimum stiffness. So whether your spring is coming into contact or whether your node is just at the border of the vicinity, there should be a minimum stiffness to be used for the interfaces. So as I mentioned earlier, either you can go for the material stiffnesses or this is another minimum stiffness that can be used. And then there is idle. So if as we saw earlier that there are material defined where if you have a failure criteria defined on some particular material, uh, then there are cases when the element could get deleted during the simulation if it undergoes higher stresses or higher energy densities. Now in those cases, because that element or node got deleted from the system, it means that that node is no more there. And if you have defined any contact associated with that particular entity, it is a donkey task for the solver to search for if that particular deleted element is still coming into contact with anything else. Now that is really something not needed, and that is why this idle exists. It just takes care of all such cleanliness drive. So if any element is getting deleted out of your system, then it will just make sure that that element is also deleted from the contact interface, and it will no more check for that particular element. Now some important gap definitions. So we'll first move towards what are the options available inside iGap. So some typical terms or important terms to look at: GM, which is master element gap. Now GM, which is master gap as shown in the picture, It can be by default t by 2, where the thickness t is equal to the thickness of the master element. uh, if it is shell element component. For 1D it doesn't even apply. For brick elements or basically solid elements, the GM has to be 0 because there is no thickness to be applied on the solid elements since they are already covering for the thickness. Then similarly the GS term, which will be 0 if the node is not connected to any element, or it can be 0 for solid element as well, or it can be thickness by 2 in case of shell elements, where T becomes the thickness of the slave surface, or it can be half of root of S, whereas S is the length of the truss or beam element. Now that means that slave node can also be a part of some spring or some 1D element which is coming into contact with a master surface. Now in that case, the slave node gap for that particular case will be half of root S. So for 4 mm, so for an element of 4 mm length, it is obvious that 1 mm will be the slave node gap. Physically, let's see how that can make sense. But otherwise, solver always had some default style of of calculating these things. Anyway, so moving forward, so in IGAP there are multiple options available. You can choose, just like how we had different options in while defining any property or material. For IGAP there are different options. First option, the option 0, which means constant gap. Now here in contact cards, 0 doesn't necessarily mean a default value, but 0 always means something. So in this case 0 means a default gap or constant gap, not really default gap. Constant gap is actually defined by gap minimum. As I mentioned earlier, gap minimum means that as long as your slaves are out of gap min, you are good to go. You don't have to worry about many other things. So that becomes a constant for all the contact all over the surface, and that really simplifies many of the calculation. Now those calculations may not be valid at all, but sometimes just the situation arises and people stick to constant gap. Now if there are different scenarios, now this gap min, so if you have I gap 0, this gap min becomes very important component of this. Now gap min always needs to be defined. If it is not defined, then it says that gap min will be calculated with this particular formula, which is minimum of master thickness and the smallest side length of all master segments. So basically gap minimum will be all dependent on what the master surface says. So let's say for a typical master surface of 5 mm thickness, with mesh size, let's say 7 mm, the gap mean could be 3.5 mm, because this 7 mm goes right exactly here, mesh size, and this term becomes 3.5, whereas where the master thickness is 5. That's why this whole thing becomes gap minimum becomes 3.5, whereas the thickness was 5 mm, so 2.5 should have been the ideal value for any gap min, but that is not really the case. So always it is a good idea to define some gap min. If the master segment is all brick or all solid, then length of the or average length of the or smallest side length of the master brick segment divided by 10 becomes the gap min, and that is always a good idea than sticking a node onto the surface directly. Going forward, now this picture would exactly tell you what is exactly happening in when we select the constant gap. all the slaves will be exactly maintained at the constant gap, and that is all dependent on the TM, which is all dependent on master surface. So as I mentioned just now, if you had 5 mm thickness and 7 mm mesh, still because this gap min became 3.5, it will be kept out of the vicinity with a gap as well, like actual physical gap in between the two compounds. Not really physical, but that can be a way to go in many cases. Now what happens if we change the eye gap value? If we make it 1, then the gap type becomes a variable option. Now variable gap means that now on the node to node basis, that the calculation of the minimum gap will be different, and that is exactly what it is trying to suggest. The gap varies according to the characteristic of the impacted surface. Now uh, variable gap will be actually calculated using this particular term. Now this gap mean again will be calculated from the same formula as the previous slide, that it will be the minimum of the master thickness and the half of the length of the master, or the mesh size of the master. So gap min is all dependent on what master surface is, or variable gap can be maximum of gap min or GS plus GM. Now GS plus GM, what we just saw was thickness by 2 for master or thickness by 2 for shell or slaves. So as you can mention, or as you can see here, now if there was a component with 5 mm thickness and 3 mm thickness, whereas 3 mm thickness was a slave component, 5 mm thickness is a master component. In this case, the gap min would become 3.5, whereas this would become 5 plus 3, 8. Now maximum becomes variable gap becomes 4 mm, and that is why in this case variable gap will become 4 mm, which is maximum of these two, and this is how it will be somewhat realistic in this particular case. Now again, that really depends on case to case basis. Now in many cases, depending on what level of, or what is the extent of simulation that is going on while defining this contact, if some part is already deformed up to an extent and the thicknesses have already reduced. So if you remember, we had one option inside shell element cards where we could say that the thickness change should be calculated during the simulation. Now if that thickness change has been calculated, it is possible that over one particular surface of slave, the thickness is varying on one side of the node and the other side of the node. Now in that case, this term really makes sense, that thickness of slave is the largest thickness of the shell connected to slave node. So for this particular node in the middle, the thickness on this side and this side could be different on the slave surface itself, and that is why the gap over here could be different in each and every case on case to case basis. And that is why this algorithm for variable gap becomes little expensive. It involves little more calculations, but again, because of all these calculations, the contact becomes little more accurate than what we saw in the constant gap. So as I just told you that there could be some errors while calculating variable gap as well, and this is the exact example. So slave becomes 3 mm, master becomes 5 mm. Now if you don't have any gap minimum defined, what it will do is it will stick to the value of 5 for gap min. And now when it comes to this particular comparison for maximum, 5 becomes the variable gap value, whereas 4 was the intended value. And why would that happen? Because if the gap min is not defined, gap min is calculated by this particular calculation, and it could give you 5 mm value depending on what L min is. So suppose if your L min was actually 10 mm, so you had a 10 mm mesh with 5 mm thickness, then it becomes 5mm and 5mm. So your gap min becomes 5mm. And now this calculation over here is not really dependent on mesh size at all, but this gap min is dependent on mesh size. So though this can become confusing because there was no gap min defined by the user, and that is why it had to stick to this particular comparison, and that could create a lot of issues. Whereas if this gap min was defined by the user, let's say 1 mm, uh, where I say that if this node becomes within 1 mm of this particular surface, mid surface, you should activate the contact. If I had told that, then this calculation could have been avoided, and now that doesn't change any calculation in the future. So if I had the gap min defined, then maximum of 1 and 4 would become 4 again, and that is exactly what I would suggest in the future slide. That if I had some gap min defined, because that gap min calculation didn't happen, this variable gap became exactly what I was looking for. Now, the first example I told you when we were looking at this particular formula, gap min was not defined, but the mesh size was such that gap min took care of itself. And that was really a lucky case, because the mesh size was 7 mm, it took care of itself. If the mesh size was higher, we saw that it could induce an error. And that is why to make our model robust of all such errors, it is always a good idea to specify a small gap minimum. That gap minimum in my application, I typically define it as 0.5 mm or 0.6 mm, and that is really that is really up to the one particular engineer. But yes, once we start following some practice, we always try to stick to that, and then we can change the rest of the system accordingly. So this was all about the shell elements. What about solid elements? So as I told you earlier, that solid elements, the variable gap could be L min by 10 if your gap min is not defined, and that helps from this particular slide here. Yep, this particular slide over here. If the gap min is not defined, then the gap min becomes, for solid elements, minimum length of the element by 10. Now imagine the situation where the solid element is actually having size 8 mm, whereas the shell elements are having thickness 3 mm. Now if shell element is coming into contact with solid, now this will be all governed by the solid element thickness, which and the gap will be becoming 1 mm, whereas there will be no respect to what the shell element is saying, because in this case, the way the formula works, GS would, because this is a 2 mm thick component, GS would become 1 because it is half of the slave thickness, and GM will become 0 because GM is actually the thickness of the solid element, which will be 0. Because solid element doesn't have thickness, it represents itself. So that means this will become 1 versus gap minimum was, oh, already we had mesh size 10, so fortunately we have some 1 value. That's why max becomes 1 and everything is sorted. Again, this really became the mesh size dependent thing, not really recommended practice. That is why always a good idea to specify some small gap min, so that those calculations will be avoided and everything will go as per this particular rule, and that value will be taken over here and the variable gap would become somewhat sensible. So after choosing or looking at option 1, I'll rather jump to option 3, where it has many other calculations involved. So until now we are looking at variable gap, where the variable gap will be only calculated by the maximum of gap min and GS plus GM. Now there are many cases where it is not just possible to take care of everything in the beginning, and that is really typical when you have penetrations issue in your model. Now penetration issue is not something totally avoidable, but it is something that can be minimized up to an extent. But even after minimizing, there will be some penetrations, and to take care of those, there are some formulations involved which will minimize the instabilities or minimize the energy errors. Now, energy error means instability. Uh, to minimize those, there are other options available. So this variable gap can also be calculated with I gap option 3. The formula would become maximum of gap minimum and minimum of F scale gap into GS plus GM. Now these two terms have been familiar for us, but this is something new, which is called gap scale factor. And then there is mesh size correction. So until now what we were saying is that this variable gap is kind of sensitive to what our mesh size is. Now to take care of that, they have a new formulation where we can have a scale factor to our gap, the gap calculated by the generalized formulation, and then we have some consideration for the mesh size as well. So going by the nomenclature, gap min, GS, GM are all the same quantities. Just that the new quantities right over here, GSL and GML, are actually the smallest age of the master element and the slave nodes or slave elements respectively. And then there is another term, gap max. Now you can see that gap max will be exactly calculated in the opposite way of how we are calculating gap min. Now in this case, if the gap min is already specified, even the gap max gets out of the way. So, and the mesh size correction is actually because the mesh size has been interfering our calculations until now. What they do is they consider a percentage of mesh size. So if let's say the mesh size has been 10 mm default for both of the surfaces, we consider 4 mm as the mesh size factor, and that way this whole calculation of the variable gap becomes somewhat sensitive to rest of the terms, and it becomes little more robust. Now in this case, if you see with the variable gap and I gap 3, what it has done is, though the master surface had some boundary limit defined around it, because there is a gap scale factor which is always less than 1, the gap scale, so the ideal gap would represent the blue dotted line. Because of the gap scale less than 1, or let's say it is 0.8, then these nodes can penetrate up to 0.8 of this particular length. So the nodes can reach up to here. Now this gap is particularly defined because of the mesh size, and that way we are trying to make sure that all the factors which are involved in the meshing as well as contact definition are considered, are respected, and in the end we are still getting a physical gap or practicable solution. So there are cases when even after meshing, because of some meshing inaccuracies, or because of while doing some quality checks, we moved some nodes here and there, or there are cases when while creating the CAD itself there were some issues in the model and there were some intersection within the module. That becomes an obvious problem for contact interfaces, because if your slave node has already passed through the surface, it confuses solver what to do in that case, because there is a whole segment which is going through your surface, and that is not really physical, that is not really possible at all. What to do in that case? So to fix that, obviously the solver would try to push out of the master node or master surface, and that is exactly what this interface is going to do, or interface force is going to do. And if you remember, that can induce some energy errors as well. So again, will that be a good idea to leave those while doing the simulation? Not really. So it is always a good idea to remove these manually, get rid of these initial intersections, so that your simulation doesn't run into issues right away at the start. So to remove these intersections, there are few tools available inside HyperCrash and HyperMesh. We'll eventually look at them as well. But in a general sense, if you see that some part is intersecting into another part too much, I would simply translate or move that node out of that part manually and then worry about whatever happens later. Because sometimes even these tools may not be very accurate in deciding which part to move. Sometimes what happens is, now I know, let's say from my experience, that it is more probable that the slave node or the slave surface is wrongly meshed, or there are some issues with the slave node or slave surface modeling. Now in that case, that algorithm could also lead to moving the solid element downwards so that the interference will be clear or intersection will be cleared. Now is that really a physical solution? No, because computer won't always know what is wrong here, and that is exactly why an engineer should use his judgment and see which side is the culprit, and that way he can better decide which nodes to move. Now there are options in the intersection tool inside HyperMesh and HyperCrash, whether if you want to fix some component while removing some of the intersections and penetrations, and that works most of the times. Sometimes it may not work, and in those cases you may have to stick to some manual methods. Now this was about intersections, that is when the slave node has completely passed through the solid surface or solid meeting surface. Now for shells, it has really passed through the surface. For solid, it might have entered the element, or it might have gone through the element as well. Whereas for penetrations are a very natural phenomenon that happens purely because of the discretization. It may not always happen because you have modeling errors or you have CAD errors, but it is only because if you choose, let's say on the fillets, if you choose very coarse mesh, then it is very typical for fillets to undergo some initial penetrations. Now in the picture itself, it is very much clear that there are two meeting parts which are connecting on a fillet as well. Now because of the discretization, while meshing, I mesh only one element over here instead of two. Now if I have only one element, I see that even this fillet is being meshed with one element. Now because of the definition of the gap itself, it creates the zone around both the components, and this is the exact area where it says that, hey, there is some penetration inside the model at the beginning itself. Now to remove those penetrations, either again there is penetration removal tool inside HyperMesh or HyperCrash, or we can tell the solver to remove those initial penetrations using some repulsion force. Now this repulsion force will be very much proportional to how much penetration has happened. Now if you have seen that graph earlier, that penetration force would really depend on one particular factor, this particular factor. So if the penetration is too high, this force will be too high as well, and higher the force, more the energy gap or energy error. So that is why you want always to keep that in check. Now keeping that in check means following the standards over here, set over here very strictly. That means now those penetrations can be allowed up to some extent if you follow this F scale gap. So if let's say this F scale gap set at 0.8 or 0.7, that means that up to some extent this will be allowed, and whatever the repulsive force comes to remove those penetrations in the beginning, that is still under control, and the energy error is very negligible, nothing to worry about. And that is why that limit has been defined there, 0.8 or 0.7. If you try to cross that, then the solver says that okay, only these many initial penetrations are allowed, and I'll try to remove those, and in that effort it induces all those energy errors. So it is a good idea to follow the best meshing practices in these cases, or even when you have initial penetration, it is always a good idea to make sure that there are no initial penetrations as per your variable gap factor. Now that we'll see when we are trying to use the uh, penetration removal tools inside HyperMesh and Crash. So as far as the Radioss solver goes, the internal methods inside solver to remove any penetrations which are existing initially, there are different options available. First of all, it would we can simply say that don't worry about it at all. Whatever it is there, just keep it as is, and if it tries to penetrate further, then only push it out. Otherwise, just keep it as is. So that means the option 0. Or then there are different options. So uh, with option 1, you can simply deactivate the nodal stiffness. That means that the initial spring which tries to push that particular node out of the vicinity, uh, the stiffness will be minimized so that the force doesn't go too high, but again that can induce some accuracy issues. Then other way could be deactivation of the master stiffness. Now that means that the spring stiffness, which is there by default, it is dependent on either the master stiffness or the slave stiffness. Now if you decide to cut down the master stiffness for that particular case, then that would affect the stiffness of that particular spring as well, which forms to depenetrate that particular node. Now if that stiffness is reduced, the energy error will be reduced. But though the energy error is reduced, because your master stiffness has been changed, your accuracy of the solution again becomes an issue, and that is really more like creating a hole in the contact. Now because you don't have any stiffness there in the master, that particular node which is inside the penetration zone can literally penetrate through the master without much worrying in the later stages. Now, third option could be automatic removal of the initial penetration, and that means it really goes on the encounter mode. It sees that there is a node in the penetration zone, it will simply remove that node or delete that node from the system itself. Now, deleting the node is not really a best practice, is it? And that is why it says that it is very dangerous to use, and it may destroy your whole model. If you have wherever you have initial penetration, that will be deleted, the node itself will be deleted. Or then you can say option 5, the gap is reduced. Now that means whatever the gap we have set earlier using igap, whatever variable gap we have set with all this calculation, uh, this gap will be reduced to match the initial penetration, and just to say that hey, whatever the penetration is, I'm good with it, and then I have adjusted my gap so that uh, if that node penetrated node tries to move inside further, then only I'll try to push it out, otherwise I'm fine with wherever it is right now. Or the option 6, which happens to be another or best option, in fact, the gap is reduced and scaled. That means that this initial gap, let's say if the initial gap becomes 2 mm or 1 mm, and you are having a penetrated node by 0.2 mm, that means you have practically only 0.8 mm gap if you don't want to depenetrate that node. That means that gap needs to be reduced. So by option 5 you would simply reduce it to 0.8, but by option 6 you would first reduce it to 0.9, and then for that particular case or that particular node you will scale it. Now the scale becomes exactly from option 3 value, this F scale. That is exactly where we are trying to say that some penetration will be allowed in the first place, so that we don't have to worry too much. So whatever is there, even inside this particular limitation, that will be pushed out. Now that doesn't involve too much operation or too much energy error. That is why it can be accepted as a good practice. And this is exactly what it is trying to suggest here. That with inactive 5, now first of all, this is master segment. It has some initial gap defined with it, and there is a slave node which has penetrated into that initial gap. This P0 is the initial penetration which defines this particular distance. So now the gap remaining is only gap minus P0, which is remaining gap from slave node to master segment. With gap or inactive 5, it will say that the gap is exactly what the slave node says, I'm fine with it. Or gap 6, inactive 6, or inactive 6, what it will do is whatever the gap is, it will reduce it further or scale it down further to this particular green line. And now what will it will say for this particular node, if it tries to move even inside this green line, then only I'll push it out. Otherwise, for this particular node, I'm fine with this particular region. Now this is a big adjustment as far as the rest of the contract goes, but to reduce the energy error, this happens to be the best practice for now. And that is why it is trying to suggest that to minimize that effect or that error involved while using inactive 6, to do that, this P0 should not cross this particular value. Now it crosses that particular value, after that the contact really becomes non-physical, or the energy spent in shooting that node out becomes really high, and that is why it can create contact stability issues. That is why this 30% of the initial gap means 0.7 of the initial gap, or 0.8 to be called at 20%. So in many cases, let's say in my day-to-day life, I usually try to use it at 15%, 20% or 10%, than going for 30%, because 30% is like really the border case. If you even mess a little more about this, you will be in a big trouble with the contact stability, and that becomes really difficult to trace out later on. So as we mentioned earlier, this resistive force is really a function of penetration, and that can be calculated as well. So this, though this becomes the mathematical formula for this, this resistive force can actually be seen in the output file. So when you plot the graphs in hypergraph, there is a contact force card or contact force output which is available globally or as per the contact. So if you request the details on some contact, it will always give you normal force or friction forces, and this is exactly how it is those forces are calculated. So if you see any jump in that particular contact force, you can say that the penetrations for that particular time zone were too high, and that is exactly when the contact force jumped up. It tried to move those nodes out, and then it came back to normal. So it is very typical for the contact force to be very much full of spikes. And now this resistive force really depends on how your algorithm is for calculating this particular stiffness. So as I mentioned earlier, if this is the slave node and this is the master segment, there is a spring that forms in between. But then there are options where the stiffness can be, or this the resistive force can be completely based on this some spring stiffness, or it can also involve some damping. Now both the stiffness and the damping can help us avoid the motion of this red node into the blue zone. And to discuss or to calculate that force further, there are obvious formulas to calculate that. But then in our case, we really stick to I stiff equal to 4, where it really sticks to the K0, which is the minimum of stiffness of master and slave, and we always try to neglect the viscosity of the contact nature, because that doesn't really happen in the crash impact analysis. as I mentioned in the very first class, there is always some degree of damping inside a car, but that doesn't really apply during crash worthiness analysis, because because the crash is such a rapid process that those dampings don't really matter anymore, and that is exactly why that doesn't need to be calculated right now, and that is why we'll neglect this C for now, and this F will be completely dependent on K into P, and this C into dPdt will be completely neglected. So now you know which is the significant formula to calculate the resistive force, and this is always visible in your output files. Now coming to the next thing to be studied inside type 7 iStiff. Now there are different types in which we can calculate the contact stiffness or initial stiffness. K0, the type 4 K0, which is minimum of master and slave. That happens to be the best practice, because it is very obvious that if you are pushing into a car cushion, though your hand could be much stiffer against the car cushion, which is foam, your contact stiffness should always be dependent on how stiff your foam is, and that is exactly what it is trying to say. Now it could be the other case. Now you have your hand resting on a table, and now someone with a pillow is trying to push on your trying to press your hand with a pillow. Now you feel that pillow on your hand, but in this case master is pillow, your hand becomes the slave, and because the master stiffness in this case is lower than your hand, and that is exactly why, again in this case, the initial contact stiffness should be the minimum of the two meeting ones, and that is exactly why the initial contact stiffness should be dependent on the pillow or the cushion and not your hand. So this type 4 becomes for eye stiffness becomes the most recommended practice. Rest of the practices are quite relevant when we are looking at some other applications, not something for crash. So good to go for now. And as I mentioned earlier, we are going to neglect the viscous forces for now, because that is not really relevant in the crash applications. There are other applications in physics where this could be applied. There are many fluid simulations which can be done using Radioss, and that could be one area where viscous forces could be important. Now, as I hinted earlier, the type step computation for this particular interface. Well, so time step becomes really drops down depending on how much penetrations you allow. If you have very strict penetration zone around your master surface, then the time step remains almost constant, but as the penetration happens, it can reduce all the time, and that particular time step for nodes is dependent on this particular formula, whereas for kinematic time step, which is contact time step, I would say, that is dependent on this particular formula. So usually, though we are targeting, let's say, 0.5 microseconds time step for all over the solution, it is a very typical practice to allow a lower time step at the contacts without having to worry about it. So coming towards the end of type 7 contact, there is one last criteria or entity that needs to be selected, idle, which I mentioned earlier, that if any of the linked elements is deleted from the system, then it also needs to be deleted from the contact definition, and that is exactly this idle equal to 2 will do. But with idle equal to 1, the master segment is removed when all linked elements are deleted. That means Just a second here. Yeah, so the master segment, well, so as soon as one of the linked element gets deleted, it is essential for the master, or it doesn't make sense for the master segment to be in contact anymore, and that is exactly what it is trying to say over here. In case of one, if that doesn't happen, then again it is little less useless. With idle equal to 0, no update, it absolutely becomes dumb that free nodes are kept around, and that is why it tries to search for this contact all the time, and that can lead to instabilities in the simulation. So to sum up the type 7 contact, uh, we said that I gap should be equal to 2 or 3, uh, where the variable gap should be taken into account. I would say that we should stick to 3 than 2. Now that really depends on engineer to engineer, but this is something that is mentioned on alter website, so this is what I would suggest for now. But in my personal cases, I like I gap equal to 3. Gap minimum should be at least 0.5 mm all the time. It should always be defined. If you leave it 0, it can lead to instabilities. In Active 6, that means what to do with your initial penetrations, and that is a good idea to keep it at 6 or 0. I step equal to 4, we just saw what it means. And then minimum stiffness for contact to avoid too soft contact, and this is really a good idea to make sure that the spring which is trying to push out the slave node, it always has to have some minimum stiffness. Before changing its stiffness due to penetrations or anything like that, it should always start from 1 kilonewton per mm or 1000 newton per mm, which is exactly the same. Then idle equal to 2 and iform equal to 2, we just saw what exactly that would mean, and that becomes the recommended practice for type 7. Now after that, we can study the non-linearity, advantage, disadvantage, and limitations, but that I'll keep for the time when we actually meet in the class. So that's all for this recorded class, guys. Thanks a lot if you're watching this video, and with this I'll conclude the session. See you soon in the class. Thank you.